the U-substitution is a very important method of evaluating integrals. So when do we use the U-substitution to evaluate integrals? So let's take, for instance, if we have this example, the integral as you can see this example, here we have this expression, and this expression has 4 as an exponent. And here, the expression here, it has 3 as an exponent. By differentiating this expression, we are going to get this expression, right? Which can be able to cancel this one. So that is a relationship that is between this and this, right? So based on that, we can determine to use the U-substitution to evaluate this integral. So let's give another example. Here, imagine if we have the function 7x 5 sine x raised to the power of 6, and you are told to integrate this. How do we determine that you need to use the U-substitution to evaluate this integral? By looking at this expression, here we have 7x raised to the power of 5, and here we have x raised to the power of 6. By differentiating this portion, we're going to have x raised to the power of 5, which can be able to cancel this one. So that is the reason we are going to use U-substitutions on this integral, right? So now let's start solving the problem. Imagine if we have this integral. So how can we evaluate this integral? Now, as you can see, the relationship between ln x and the denominator is x, right? So we need to set u, in this case, equal to ln x. So we need to differentiate ln x, which is going to give us the u 1 over x. By the way, if you are differentiating the natural logarithms, this is how we need to differentiate natural logarithms. Let's say we have ln of 3x plus 2, right? And you want to differentiate this one. What you have to do is to get u, and you want to differentiate this one. The formula is going to be u prime over u, all right? So u in this case is this entire expression, right? U prime is going to be the derivative of u. So in this case, the derivative of u is 3, and u is 3x plus 2. Another example, if we have ln 2x plus 3 is going to be the same. Here is the u variable, and u prime is going to be the derivative of u, which is this one. It's going to give us 2 over 2x plus 3. So that is how we can differentiate a natural logarithm problems. So now back to this problem, dx. We can now solve for dx. We can cross multiply. Dx now is going to give us x du. As you can see, x in this expression, this s is going to cancel with the x that is in the denominator. And now we can rewrite this expression as u raised to the power of 8 dx is this x du over x. We can cancel these two x's. We'll now have the integral of u raised to the power of 8 du, right? So now what can we do next? We need to use the power rule. And the power rule is, if you have a variable called x raised to the power of n, you have to add 1 and divide by that variable plus 1. So for instance, if you have x raised to the power of 2, you have to add 1 and divide by 2 plus 1. So now in this case, we can say the integral of, we can say u raised to the power of 8 plus 1 over 8 plus 1 plus the constant of integration. So by adding the exponent, we're going to be left with u raised to the power of 9 over 9 plus the constant of integration. We can substitute the value for u, which was, in our case, ln x. So by substituting ln x, we're going to have ln of 9x all over 9 plus the constant of integration. So this is the final answer for this problem. Now let us get another problem again. So how can we evaluate this integral? Our first goal here is to identify the relationship between these two expressions, right? As you can see, we have e raised to the power of 5x. That is the relationship that we have, right? So now what can we do? Should we set this equal to u, or should we set this equal to u? As you can see, if we differentiate this one, the denominator, we're going to have e raised to the power of 5x, which can cancel with the numerator. So in that case, let's set it equal to u. So we can let u equal to 1 plus e raised to the power of 5x. We can differentiate u, the u. If you differentiate a constant, is 0. So we're going to be left with e raised to the power of 5x times 5. We can differentiate log base e raised to the power as, imagine we have right? We can differentiate this as e raised to the power of x times the derivative of the exponent, which is 1 here. So that is the reason that d over dx of e raised to the power of x is equal to e raised to the power of x. So if you have d over dx as e raised to the power of 2x, it's going to be e raised to the power of 2x times the derivative of the exponent, which is 2. So this is going to give us 2 e raised to the power of 2x, right? So in our case, here, we have e raised to the power of 5x times 5, which is e raised to the power of 5s times the derivative of 5s, which is 5. So now we can solve for dx by dividing. can cancel these two. So we'll now be left with the x is equal to du over e raised to the power of 5x times 5, right? We can now substitute. By substituting, we're going to be left with e raised to the power of 5x. The denominator is going to be set equal to u. Then the x here, we can say du over e raised to the power of 5x times 5. So these two can cancel. We'll now be left with the integral of 1 over u du over 5, right? So now we can send this 5 across, that which is going to give us 1 over 5, the integral of 1 over u du. So there's another rule that if you have the integral of 1 over u is equal to ln u, right? So we can now say that 1 over 5 ln u plus the constant of integration. We can now substitute the value for u, which is going to give us 1 over 5 ln of 1 plus e raised to the power of 5x plus the constant of integration. So it is necessary that you don't forget about adding this constant of integration.